Okay. Good afternoon. I welcome you to this lecture in optimization. And as usual, I like to recall what we did last time so that we get into the topic, and I myself. So we first finished the chapter on convex optimization, and we introduced some very interesting class of optimization problems, which is called semi-definite programming. And during the last week, Dimitris and I decided that we will give you even one exercise on this semi-definite programming, a formulation, so that you get a bit of the spirit of that world, because we will not do it later. But it is something that a lot of people in optimization are very excited about. Okay? So that was the first part. And then the second part was we introduced the Lagrangian function and duality. And this is the chapter in which we are still, and which I want to finish with an example. Instead of recalling the definitions of dual function, of the Lagrange function, and so on, I will just go through one example. And this example is called dual decomposition. And I want first ask you a question in order to motivate it. Did any of you read a famous book that's called The Invisible Hand? Well, it was not the book. The book was called The Wealth of Nations by Adam Smith. It's an old book from many centuries ago, which it was a Scottish scientist who maybe laid the foundation why we are now sitting here in a prosperous country, because he basically derived the rules that made distributed optimization possible in our world, and that leads to the wealth of nations, as he proved in his book, so to say. It was a scientist who was explaining how politics should be so that people get rich, on average. Yeah? And in fact, the underlying principle, what he called the invisible hand, this fact that if people just start to exchange and negotiate and make contracts and pay money to each other and all these things that you might find good or bad, but that these things are really useful in order to find an optimum and to develop, so to say, the human economy further. And I want to actually make a connection with Lagrange duality. you will actually see this quite quickly. So let me just give you an example. I want to discuss the question, how can we share a limited resource among us? Yeah? Let's say not among us here in the lecture, but let's look, for example, at a city like Freiburg, where in the city we have a limited space of living spaces. I mean, there is a limited amount of square meters where people can live. And as you notice, they are very unequally distributed and so on. Some flats are even empty. And this is all maybe not optimal. But so you could have the idea that a perfect allocator, maybe our mayor, of course the mayor doesn't have the power, fortunately, to distribute our flats to people. But you could imagine that. There would be a central distributor that just says, I give things to everyone depending on the needs. But this is the question, what are the needs, right? And that's, of course, the main difficulty. But we could even make the situation more optimistic, and we assume the mayor knows how much pleasure or benefit you and your family with these 5 kids or whatever gets from living in a flat of that size, right? So let's assume there is even perfect knowledge about the objective functions of all of us, and then the mayor or the central distributor just has the aim, let's make an optimal allocation so that the average happiness is maximized. Because we are minimizing, we just minimize the average unhappiness, okay? It's just a cost. This is just a definition. And I want to state this problem a bit mathematically. It's example 4.3. It's called dual decomposition. And I hope that from time to time you happen to make the connection with prices and with limited square meters. Let's assume we have, so to say, this average unhappiness for each family, let's say, and xi is the amount of square meters that they have available in order to have a life. And yi are some other variables that they might have at their disposal. For example, they might be able to have some of an extra garden in the Black Forest, or they have relatives in the Black Forest where they get where they have to travel, but they can get pleasure from being in the green, so they don't need such a big house here, and so on, right? So these would be our objective function, and we want to minimize it. As I said, we just minimize over all x and all y. If I don't write an index, then I mean all the vector of all these things together. This index I goes from 1 to n. Big N is the number of households, let's say, in a city. Yeah? And the constraint, subject 2, is that the total amount, I write it like this, there is the maximum amount of square meters in Freiburg should be bigger than the sum of all the square meters of that are used. Yeah, of course, we might easily say, but if it's optimal, this should be equal, right? So, I mean, otherwise there would be unused square meters. This is something we might conclude later, but at the moment this is the setting. We have a cost function which is individual for all people. They have decision variables for themselves. So these xi is element in R, let's say. It's just a scalar number. But the yi's are element in R, ni. So every person has a different set of optimization variables, yeah? Or every household. This is the problem we want to solve. And assuming that we have this perfect knowledge, we could actually just solve it and say, yeah, but you have this family there, so you should get less square meters here. And then somehow this will, on average, make the whole population in Freiburg happier if you take only this very small flat. And the other people that don't have a family in the Black Forest, they need a garden or something like this, right? So you could make this trade-off from the central distributor. I don't talk about the political problems that this would have, of course, right? But I want to just assume that would be a perfect and nice person who wants to distribute these things, and he does it in a very fair and Solomonic way. And now we want to look at this whole problem from the optimization perspective and make a few assumptions which are maybe a bit abstract. Already this is abstract, right? Let's make, first of all, let's just construct the Lagrangian function of this whole thing. Yeah? So what would be the Lagrangian function? It's a function that now depends on x and y, and also on some multiplier, which I call mu, because mu was the multiplier for inequalities. And it is the sum of all these things, and I directly write it in this way. I have 1 to n, and here I have fi, xi, yi, and I have a contribution from here. It comes with a double minus sign, right? So we take a plus sign here, plus xi times u. That's the contribution that we get here, and I make the sum around it. So then I don't have to write 2 times the sum sign. And at the end, I get this remaining thing minus mu times m times mu. This is the Lagrangian function. And the Lagrange dual function we can always define. We learned last time we can define it for any problem. So let's just define it. What is the Lagrange dual function? The Lagrange dual function is called Q of mu. It's a scalar function. It is just a number. And in this case, mu is also only a number because we have only one constraint. Okay? So that's an interesting thing. But let's write down what is this Lagrange dual function. You remember it was the minimum or the infimum to be safe, so that we have also possibilities of non-converging sequences of the Lagrangian. So we just write it down. So it's the infimum over all x and y of this function. I need not write it again, but I can observe one thing. In this thing, I want to make sure that you appreciate this interesting observation. This is a sum of x functions depending on xi and yi, the local variables, how much space I have and how much I do other things, other degrees of freedom that I have. And this is my space again. So actually, this whole thing can be written as a sum, and this doesn't depend on my variables. So actually I can put it to the front. So this is a part that is in my Lagrangian anyway, And then I have here plus the sum I1 to n. And now it turns out that I can actually minimize over all these variables separately. xi, yi plus xi times mu I, mu. So this was a crucial step. Instead of minimizing over everything together, I recognize, because it's a sum of terms which just all depend on different variables, I mean, they're completely separate optimization problems, right? If family A looks at this, you can just solve this thing for family A separately, and then you say, I solve it for family B and family C. Actually, I equal 1, 2, or 3. And I just sum up the infima, and then I have the optimal cost. And the only connection that was made now between these families is actually via this extra term that was not present in their original cost function. So you made somehow it. What is this? It's a penalty on using space. Right? So if you would optimize over all the variables of that family, you find a different optimum than the optimum that would be there if the space was not limited. You find an optimum which is actually can be interpreted as an optimum which says, okay, I have my own unhappiness and I have a price to pay for space. And then you find the optimum. What would this family do if it would have to pay, let's say, 15 euro per square meter? Yeah, that's like the price we might very soon have in Freiburg. I hope not, but it might. So you see that this optimization can be given a meaning. So this optimization is now can be done independently, and in the case of the economy, it is actually even done by all the families separately, and it's this mu which will connect between them. But also in algorithms, when we do optimization algorithms, there is a family of methods that are called dual decomposition methods, and they use this fact that you can actually solve a lot of optimization problems independently, for example, on parallel computing architectures. So you could imagine that even the central planner says, okay, let's maybe, because there are so many families in Freiburg, let's somehow distribute the computations and give a big cluster, and then on this cluster you just say, the only thing actually that I as a central planner need to find is the right price, and then I let all these lower level optimizers run, and I find the minimum. Actually, it's not the minimum that you need to find. You want to find, because we are now in this dual setting, what the central planner would have to need to find is actually the maximum of this, and we would then also only know that it's a lower bound on the optimal value. So it's not really solving the problem exactly, but we have already encountered that for convex optimization problems, it actually is equivalent, so we actually get the same value, and by the way, also the information about the solution. So let's assume now convexity, which is of course something we don't need to do to formulate the dual, but it's more useful when we assume convexity. So let's formulate the dual, maximize Q of mu, subject to mu bigger than 0. And the only variable is mu element in R. So in this case, it would be extremely simple. What we could do now is actually just a grid search. We set the price to 0. Yeah? We see what is the dual function, and then we increase the price a bit, and then we find the optimal value. That will be a concave function, as we know. This thing, by definition, will be a concave function. So at some point, we could just have, if this is mu, and this is Q of mu, so there will be some, maybe, actually, that will become, depending on these cost functions, it might be that we get an infinite for zero price, and then there's somewhere a maximum, something like this. And somewhere there will be the right price, that is called mu star. And now I want to analyze what happens when we have the right price and what actually optimality of the Lagrange dual function means. I think I will do it a bit less complex than in the script. Details you can read in the script, and also you can detect one error which I found, which I will not repeat, of course. So what I want to understand is actually, we will assume actually that this constraint will not be active, so that the price is not zero. I mean, that's we can exclude probably, right? The optimal value will not be that there is no price for square meters. So let's assume we are here in the interior, and then we know that the optimality condition for this problem is, because it's a concave problem, the optimizer will have to satisfy that the gradient of Q at mu star must be zero. Yeah, that's the optimality condition. And I want to understand what this optimality condition actually means. And this optimality condition, we have to look into the function itself. So let's look, what is Q mu? If we look at this whole thing, I will have to make a little notation. I will assume that x I star of mu is actually the optimal solution of problem I for the price mu, for the multiplier mu. yi of mu. So these are the optimal solutions, and then I plug them into this thing, and then the inf can go away because it's the optimal solution. So what this is minus m times mu plus the sum of fi of xi star mu and yi star of mu plus xi star of mu times mu. I hope I didn't do anything wrong. And now I made one more assumption. I should say also C1 of all the functions fi. Yeah, so that I can actually use gradient being zero as an optimality condition. Because then I know that by optimality of these lower level problems, I know that the derivative of this whole thing with respect to the variables x and y will be zero. Yeah? So here we have this thing. And if I call this, I can give this a name. Maybe I give it a name for a moment to have it a bit brief. It's phi of x I, it's phi I actually, yi, and mu. So this is a function. I just make it for abbreviation. And what I know from optimality is something, namely, because these xi's are optimal, what we know is that the gradient of this phi I with respect to xi is zero, and that the gradient of this phi I with respect to yi must be zero, because these local optimizations need to be satisfied, and we have differentiability. And the interesting thing is now, because this whole thing, of course, the xi depends on mu, the yi depends on mu, I can actually write the derivative. This is a scalar function, so I could directly write dq by d mu of mu. So what is this derivative? It is actually here, we see it directly, it's minus m, okay. And here it is a bit more complicated, and that's why I had this extra shorthand. It will be the derivative of this whole term with respect to mu. Yeah? But what will it be? It will be the derivative of d phi I by dxi times dxi star times d mu. Because it implicitly depends on mu, right? The same for d phi I with respect to dyi, dyi star with respect to d mu. And the last thing is the explicit expression d phi I by d mu. So that's actually the direct partial derivative. And the beautiful thing is now, because this thing is zero, that's actually the derivative, this is the transposed gradient, so this thing is zero, this thing is zero, and the only non-zero thing is this. So the only thing which remains is the direct dependence of this function on mu, which is only here. So all the other is indirect via the optimal variables. So the partial derivative of this whole function can be easily written as just the partial derivative with respect to mu. And we get, I write gradient again, it's the same symbol, just because it's a scalar, we don't need transpose signs here. It's equal to minus m plus the sum of 1 to n, the partial derivative of this function phi with respect to mu, but that is just xi star. Partial derivative with respect to mu. So xi star of mu. What is this? So that's the gradient of the dual function. Do you recognize something? We say this should be zero at the optimal, when the price is optimal, when we have this maximum there, the dual function, the maximum of the dual function. Exactly. All the square meters of the city should be somehow allocated to families. I mean, if they use it is another question, but everything has an owner. There's nothing ownerless. And they have to pay some prices. So there's a little, I don't want to justify the economic order in which we live, but I think this gets close to something like this. So we see both some justification for property, let's say, and we see both a justification for prices in some sense. I just wanted you to see this connection and to know about this technique that's called dual decomposition, and which is due to the fact that we have a lot of local agents, so to say, that's how you call it in this language, which share one common resource. In this case, it would be just one. I should say that, of course, we could also make m vector valued, the big M, and then share maybe not only square meters, but we could also share electricity and water and so on, and then everywhere we will have the same thing. Actually, with air you could even do it, and with air usually we assume that there is no price on air. I mean, I breathe and I don't pay for it, right? And I'm very happy that I don't, because we assume that this resource is unlimited, so to say. And at the moment when we realize that resources are not unlimited, at that moment we should also think about putting a price on them. And I think, I stop advocating my policy convictions, but I think that we should have a price on carbon dioxide in this society. Okay, because the amount of carbon dioxide that we want to bring into the atmosphere as a world population is something that we don't want to be used ad infinitum. Okay, so let us stop here with motivating a bit the meaning and also the beauty of duality. So you have heard about duality, you have seen that there is some connection of these Lagrange multipliers with prices, and sometimes these multipliers are also called shadow prices for that reason in the optimization literature. So there is a lot of connection also to economics. But I'm not an economist and I don't know enough about it to make really strong conclusions, but I can just tell you that a lot of economics people know a lot about optimization, of course. What we want to continue now is the next part, actually. So we are at a very important breaking point of this lecture, because the next part starts now, and it is called unconstrained optimization. And because I find it so important, I gave the name to this part and Newton type optimization. It's funny, I just realized Newton, also a British scientist, when was it, 1600 something, end of the 17th century, might have been at around a similar time as the previous guy called Adam Smith. Completely different fields, but Newton, as you will see, invented a beautiful method that we still call Newton's method, which we use a lot in optimization. Before we actually go to the algorithms, which is the main aim of this course and which we will do maybe already today, I want to go into understanding the optimality conditions for the general problem. So we will have chapter 5 on optimality conditions. It's the first chapter. So it's the optimality conditions for unconstrained optimization. So the setting is extremely simple, and let me just recall what is our setting. The setting here is unconstrained, so our problem is minimizing a function f of x, where x is element in Rn, and that's it. There are no constraints, so we can forget about Lagrange functions because there are no constraints. Yeah? There is no Lagrange function, or it is actually the same as the original one, so there is nothing to talk about duality here. It's just unconstrained, easy and simple. There's a little catch, because sometimes we want not to optimize over the whole space. There might be functions like, for example, this function that goes to infinity when we are at 0 and then does something here. Yeah, that would be, for example, the function, which was it, 1x plus x. Yeah? That function also has a minimum, and we will probably be able to find it with an unconstrained algorithm because the minimum is in the unconstrained interior. But then we cannot formulate it like that. And what we will actually assume is that there is a domain. So we will replace this Rn by a domain D in Rn. And we make the assumption that it's open. So we are only interested in finding a minimizer in the middle of this domain, and we allow that the function is not defined outside of this domain. But still we call this unconstrained optimization because there is no explicit constraint that we want. There's just one function we want to minimize, and it happens that this function we cannot evaluate at some other points. So that is the general setting, and the first thing you might know, but let us just recall these things. So the first theorem is called first order necessary conditions. We had it already for convex problems. Condition, or condition in this case for optimality. But we give it an abbreviation that I will use a lot, is FONC, first order necessary condition for optimality. So when you see FONC, that's the first order necessary condition. Okay? And what this condition says is, if you have a local minimizer, if x star element in D is a local minimizer, or minimum point, maybe we should use that word more correctly, because a minimizer could also be the person that minimizes, right? And this is the point that minimizes, so it's a local minimum point. And f should be a differentiable function, so otherwise this whole thing doesn't work, and f is element in C1. What will it imply? Then this implies just that the gradient of f at x star should be, which value? 0. So that's obvious, you have heard that many times, but because we are now in a mathematics lecture, we want to prove it. Yeah? So it's nothing is obvious for us at the moment. So let's just, because it will also allow us to get some definitions clear. So how do we prove it? We have to somehow see, if that's not the case, we have to disprove that it's a locally optimal point. And the intuition is quite clear. If there is a gradient, then there is somehow a way that we could go down, right? So let's make this distinction. So we will actually prove that if this is not the case, then it cannot be a local minimizer. So assume for contradiction that gradient of f at x star is non-equal to 0. And what we will now define is a vector which is, maybe you don't even want to call it like this, but I define P to be the negative gradient. Yeah? So P is element in Rn. And whenever I write P, and I will write P a lot of times in this lecture, I mean a vector in Rn. And in this case, this vector P is in the negative direction of the gradient. Intuitively, you have this gradient. The gradient always points to the direction of upwards. So the negative gradient points into the direction of downwards. And I want to actually define one thing on the fly. It's actually a little box in between the proof. P, element in Rn, is called a descent direction if nabla f at a point x, if this gradient times p is a negative number. Okay. The intuition here is that this is, I will actually give the intuition in a minute in the proof, but I just want to say this is a descent direction. By this definition, because if you take P times this nabla f, then it is actually minus nabla f. And that's smaller than 0. Okay, it's trivial, but I just wanted to make this a little definition because, yeah, if the gradient is not 0, we can find this p, and this p is a descent direction. And why do we call it a descent direction? Because it will actually lead us down. And how do we prove that it is something that leads us down? We will just regard f on a line which starts at the optimal point, or the point that is not optimal, times t times p. And when I write t in this lecture, t is usually nearly always a scalar. So this thing is what we are interested in for sufficiently small t. And for sufficiently small t, this will be defined because our domain is open, so there's always a direction around it. And we can actually use Taylor's theorem. Oh wow, Taylor is another British man from centuries ago. So here's a lot of British mathematics. It's funny. It's maybe only today, but anyway. So we have f of x star plus t times nabla f of x star transpose p, which is the first part of the Taylor series, but I don't need even the first part of the Taylor series. Sorry, I'm a bit confused at the moment. I just know from Taylor's theorem that there would be some value between, which might be smaller than theta, is between 0 and t. Yeah, so it's some value where we will have that's the mean value theorem actually. So the derivative at some point, this is the derivative of this function. Maybe this is the little thing I might have said before. So what is this f, this total derivative of df by dt? It would be the derivative of this whole thing with respect to this argument, and then times the inner derivative, which is this thing, right? And so we will have nabla f of x plus tp transpose times p. That is the derivative of this whole thing, right? And what does the usual mean value theorem say? It just says that there is some value if you just have a derivative here. Hey, I'm so confused. I'm sorry, I ate too much at lunch, I guess. So the formula is definitely correct, yeah? And the visualization of that formula is that we have here the point f of x star. Here we have the point with t. So this one is that one. This one is this one. And then what this theorem says is that there is somewhere on the way the point where this derivative will be taken. That's exactly what I want. Yeah? And this is the derivative here. Yeah? And then we have the identity. And what I want to use now is actually that the product here, nabla f times p, was negative. So when my t is small enough, then this thing will be by continuity. This expression will also be negative. Yeah? And so this whole thing will be smaller than f of x star. So this will be smaller than 0 for t small enough. Okay. So this is a complicated way to prove a simple thing. And I have another definition that I didn't want to forget, and that is actually that we call a point where this condition holds. If nabla f of x star is 0, so if it's not a descent direction, or if there is no descent direction, x star is called stationary. So a stationary point is a point which has a gradient 0. I point out, and I just want you to note that a gradient 0 can be either the nice situation that we think of, like a minimum, here, that's a gradient 0, could also be a maximum, could also be a point which is neither a minimum or a maximum. So it can be anything. It's just a necessary condition for optimality, and that's why we have the arrow in this direction. So if we have a local minimizer, then the gradient must be 0, but it's not sufficient. So there need to be more conditions later. But let's first strengthen the necessary conditions a bit, because when you see, for example, such a thing, such a situation, you might guess that already the second derivatives are maybe having something like the wrong sign. So you have a positive curvature here, you have a negative curvature here. And if you have a positive curvature, then it can be optimal or minimal, but if it's with negative curvature, it could not be. And let's make this into a little theorem, which are the second order necessary conditions. Second order necessary conditions, I will not write it, but we know what it is. And what will it say? It will just say that if we have a local minimizer, if x star element in D is a local minimum point or minimizer, then one other thing must hold, and this is that the Hessian matrix has only a non-negative eigenvalues. That means the derivative, this Hessian matrix, must be positive semi-definite. So let's also look what does positive definite mean. It means that whenever you multiply this matrix from left and right with the same vector, it will be a non-negative number. So let's again prove for by contradiction. We assume that there exists a P, yeah? So that P transpose nabla square of f of x star times P is negative. Basically, that would mean that there is at least one negative eigenvalue in this matrix. Yeah? So that is definitely not this condition. So if it's that's proof for contradiction. So if such a direction would exist, this is something that we can use now in order to prove that there will be a neighboring point which has a lower objective value. Yeah, so let's do Taylor's theorem again. And yeah, so here we do it with second order. And what we will do is we will use f of x star plus t times p in this same direction. We will have f of x star plus the first order term, and the first order term now is t times nabla f of x star transpose p. And we take the second order term here, which is in some sense the same theorem, but it's now one order higher, and we have the second derivative of f of x star plus, I call it not theta, or I call it tau, but it's basically the same meaning again, times, and I should say there's a p from this side and from this side. Because if we differentiate that function twice with respect to t, then as you remember here from this formula, this would be the first derivative. And if we differentiate it again, the other p will jump out, and that's why we have a p transpose nabla square f times p here. And here we have again with some tau, which is element in 0 and t. So it's some value in between. Okay, so this is just, so to say, a trivial identity, but what we see here is that this thing by the first order necessary condition must be 0 already. So this is already 0. So we assume it's a first order point, and we assume that this is, and then we see that this will lead to a contradiction, and the contradiction will be actually here, that this term will be negative because of continuity of our Hessian. I mean, if it's negative somewhere, then in a small neighborhood around it, this whole term will be smaller than 0. So the whole thing would be smaller than f of x star contradicting local optimality. So we see when we have a negative eigenvalue in our Hessian, that would directly lead to the fact that we can go in, as in this example, that we can go to the left or to the right side. Doesn't matter, we will go down, even though later on we might go up again, but it's of course the neighborhood which matters for local optimality. So this is also not a sufficient condition, I should say. I mean, it includes some situations, but it doesn't exclude, for example, the following. So you could have the function f of x, which is just scalar, but it's minus x to the 4. It's this function here. It looks like a maximum, and it is a maximum at 0. But its second derivative is also 0, so it satisfies this whole thing. Yeah? So this is necessary, but not sufficient for optimality. Also, by the way, this situation where we have x to the power of 3 will also have 0 second derivatives, and it's neither maximum nor minimum. Yeah? So it is something that a minimizer needs to satisfy, but which it sometimes does not satisfy. So how can we now have sufficient conditions for optimality? And one sufficient condition we had already, and this sufficient optimality condition that we know already is actually holding for convex problems. So when we have a convex optimization problem, then we know that this stationarity is enough. So I just recall that because we have proven it already. Oh, sorry, it's a new section, I should first say. 5.2, sufficient optimality conditions. And the first theorem is convex. Convex first order sufficient conditions. So that's why I have an S here. First order sufficient conditions, but this is only possible for convex problems, so I give it this name with a C in front for convex. And what do these first order conditions say? They say basically if x star is stationary, x star is not only a local, but it's actually a global minimizer. But only if f is a convex function. And it should, of course, have a gradient, so it must be C1. So that's something I just recall. That was beautiful and is extremely powerful. We used it already in some examples, but it's, of course, not always the case. And so now let's do one more condition. And this is a condition which always holds not only for convex problems, but in order to have a sufficient condition for optimality, we need second derivatives. And actually, if you look at this theorem and also how we proved it, what you would like to have is really strictly positive eigenvalues, because then you can be sure that this term will be also in the neighborhood positive. So the theorem here is called second order sufficient conditions. And this theorem says we have an f which is C2, so that's something that we need to assume. And of course the domain and so on, but if it says that if x star element in the domain is stationary and the positive definiteness of the Hessian holds, and nabla f at x star is strictly positive. So here's a strict inequality now. Strict, all eigenvalues are positive. Then x star is a strict local minimizer of f. And this thing I want actually not to prove the usual way here with Taylor series and so on, but I want to prove it a different way. And I want to use our convex optimization knowledge already. So what I will do is actually I will choose around this point. So we know that actually the gradient must be 0 because it's stationary, and the second derivative must be positive, positive definite. But that means that when we go a little bit around our point f of x star, in the neighborhood around it, the matrix will still be positive definite, right? So because of continuity, that's C2. So there exists a ball around, so that I call it B, so that for all x in this ball, for all x in the ball, we have that the second derivative, there was a square missing, sorry for that. Second derivative of f of x star of x is still strictly positive. And that means that in this ball, maybe I draw it here, this would be component x1, x2, and I have my point x star here, and I make a ball around it. This ball is so small that all points in this ball have positive curvature. That means f is convex in B. So if you would restrict your optimization to this ball, then you have a convex optimization problem. You have stationarity. So that means that x star is a minimum, actually a global minimum in this ball. It doesn't mean that it's the only global one, because that's something we didn't prove, but it is a minimum point in B. So we have proven that it's a minimizer, but what we also want to prove is that it's a strict local minimizer, so that there is no other point. And in order to see that there is no better point, we can actually use Taylor series again, and then we do something like this, f of x. I expand it in every possible direction, so I just do f of x times is equal to f of x star plus the first order Taylor series is nabla f of x star transpose x minus x star. That's the first order term. And now we have a second order term again between the 2 points, which will be 1/2 x minus x star transpose nabla square f of x star plus, and here we have to go only some way, so I call it theta again, x star, and I close it, so that's the evaluation point of that derivative, and here we have x minus x star. So again, same mean value theorem. So there exists some of these thetas. In this case, theta is between 0 and 1. And what we see is that this thing was 0. This thing is the value of the function at x star, and this thing will be strictly positive if x is not equal to x star. Right? Because there is a positive definite matrix in this neighborhood. It's all positive. So when this vector is not 0, then this whole thing will be a positive number. And so we see that it's bigger than f of x star, if it's not the same point. Okay, we could have actually proven both things using that only, I realize. So we would not have even needed to invoke convexity. We could just have said there's this whole ball. In this ball we have a positive definite Hessian, and then because the first order term is dropped, it must be the second order term which dominates, and then we have directly proven local optimality in this ball. But I wanted to point out that we have this local convexity as well, because sometimes it's giving us a good idea. Sorry? What's the question?
Yeah. X is outside of the ball.
Okay. So this is only for all x in the ball. Huh?
Yeah. So we still only show it for the ball.
Sorry?
So we still only show it for the ball.
Absolutely. We have shown everything only for a ball, and that is what local optimality says. So it's a strict local minimizer. So we cannot do anything else. If we look at derivatives and we don't have any global knowledge about our function, like convexity, then it cannot be any...
Okay, so that was just two ways to prove the same thing.
Yes, exactly. No, this one didn't prove strictness. Here we even proved strictness. So the second one was just the better way. Yeah. So this little thing is, in a sense, it's a bracket that you can use for non-strict optimality. And then it would not need Taylor series, but for the strict one I had the Taylor series again. So I think this is enough of recalling. I guess that most of these conditions you have seen before. I don't know, maybe in the scalar case or already in the multidimensional case, just from my understanding. Is this something that's treated in analysis lectures normally with multidimensional things? Okay, good. Are also Lagrange multipliers already covered there? Yeah? In mathematics. In which lecture is it? Analysis 2. Okay. Mm-hmm. And inequalities are not covered, I guess. Inequality constraints are not covered there. Mm-hmm. Yeah. And duality also not. Okay, good. Mm-hmm. I think this is where I want to make a short break, and after the break I want to continue with perturbation analysis of this problem and look at the question how stable a solution is against perturbations. Yeah? But let's first make a break until 3:05, please. Before I forget it, I want to just say a few words about the exercise sheet, the next one. It is online, Dimitris asked me to say, and it's also here. You can take a copy with you. We have two theoretical questions, which are just pen and paper questions about computing dual functions, and one MATLAB question, which Dimitris put a lot of effort in, as I have said, where we optimize actually truss topologies. So the question here would be, you have a limited amount of material, you have some connections between points in the space, and you want to build, for example, a bridge or something like this, and you want to know how thick should be the parts of your bridge. And some parts need to be thicker because it will support your structure at more important points, and some other parts can be either thin or even be absent. And so that's what trust topology optimization does. And it turns out that this problem is a convex SDP. So this thing we wanted to share with you with a very small prototype. So there are people that do much bigger and larger and more interesting problems than what we can do in the exercise. But it gives you a flavor. So these are the two things for the exercises. And there's a question.
I have a short other question.
Yes.
I always have the problem in mind of distributing, for example, if I have football teams,
yes.
which have to play a game against each other, each team against the other team.
Yes.
And on weekends over the year, and they have a game at home and they have a game the other home.
Yes.
And so on. And this problem,
yes.
I always have this problem in mind.
In mind for an optimization problem. Yes. Maybe my question to you is, this is an interesting optimization problem, absolutely. I don't know what's the optimal value or what you want to minimize in this case. Maybe travel distance, or I don't know what would be your objective function, but already finding a feasible solution is difficult for what you say. But you can help me, or not help me, but I tease you, I give a question back. In which class of optimization problems do you think this problem will be?
Yeah, this is the mixed integer.
It's probably pure integer, I guess, even, because there might be no continuous variables. Yeah. So it's an interesting problem, but many of the things that we teach here are, of course, about differentiable functions, and so they are not directly applicable here.
Yeah.
So most of this stuff is not.
It's not a problem which is related here.
Of course, it's an optimization problem, and there is some relation. Actually, the second of our questions is looking at integer optimization problems, but this course is not about integer optimization. But duality can still play an important role there, because duality is applicable everywhere. Okay. Good. As I promised, I wanted to continue with parametric sensitivities or perturbation analysis. So this is a little last section on the optimality conditions. Which I wanted to share with you because I think it's important. And the topic I want to look at is, how does the solution of your optimization problem depend on the data? Yeah? So what we could have is an optimization problem that is depending on all the data that specify your problem, they came from somewhere. Someone typed the numbers into a computer or used some other algorithms to compute them. And so they might be a little bit different the next time you solve the same problem. And then the question that you could ask is, how different will be the solution then? And this is something we can analyze with a bit of theory. And surprisingly, we can show that if these second-order sufficient conditions of optimality are satisfied, that means the strict positive curvature, that then our solution is stable against small perturbations. So that means we change a bit the data, the solution will also change only a bit, and it will not be completely different solution. And this is the setting which I want to make, is that I say that I have an optimization problem which has a variable, but it has also a parameter. Yeah, that's why it's a parameter that is our perturb parameter. So what we will regard is a function f, which depends on two things, namely on x and on a. A is the second argument. So basically f is a function from Rn cross Rm to R, our objective function. And what we want is to minimize this function with respect to x. And we look at the solution map, and we assume that these values are unique. Unique minimizers. X star, but they will depend on A. So for each A, there will be a different solution, of course. Right? If you make a different A, there will be a different solution. And so we call basically xi star is the argument that minimizes f of x and a. So that's a notation I use. It's officially actually giving back a set, but if we assume that it's unique, then we can also use this. We just say it is the point that minimizes that function. And this thing, this map is actually a map. X star is a map from Rm to Rn, right? These are the optimal values, the optimal vectors that minimize our function. This is called the solution map. So the solution map is the map that we want to analyze, and we want to analyze it based on some information that we have about the first and second derivatives of f at one point. So we assume actually, and I directly formulate it in a theorem. So the theorem will be stability under perturbations. And our setting is the following. It is a setting where we'll assume that we have, actually if you think of it, here we have a and here we have x star. Yeah? We have some value that I call a bar, and we have a corresponding value that I also called, I think, x bar, which is the corresponding optimal value. So here we have x bar. And at that point we have a local minimum, and that's the only thing that we know. And we only know the derivatives at this single point. And what I want to prove is that actually this map, x star, is somehow nice and differentiable, at least in the neighborhood around my parameters. So if I perturb the parameters a little bit, I will actually just have a smooth dependence of my solution on my data A. Yeah? So, yeah, maybe to visualize what we have here is an A coming in. We minimize, we compute something, and what comes out is an x star of A. And that's the map that we look at. So we will make some assumptions. So we assume that, this is F is a map from our domain, the same domain as before, and here we have Rm. That could be also restricted, but let's just do Rm because this domain doesn't matter so much. To R is a C2 function. So that should be a twice differentiable function. And we regard the problem of minimizing f of x a bar for a fixed a bar with solution x bar that satisfies the second order sufficient condition. That means actually that its gradient of x bar with respect to the variable x will be 0, and that the second derivative, sorry, this is wrong because it's now a function that depends on two variables. But the second derivative also with respect to the x variable will be a positive definite matrix. So these are the two things that we assume. And I think I want to continue the theorem here, so I use the full blackboard now. I continue here. And what we then want to prove is that there exists a neighborhood. So this is the neighborhood we want to look at. So something that I call N. And in this neighborhood, our solution map really exists. Of our point A bar. So then the solution map x star of A exists and is unique. So there's just unique solutions. Yeah, and solutions are unique. So the solutions are unique. And this function is also differentiable. X star is element in C1. And of course, x star of A bar is equal to x bar. Of course, it should have this property. So here's our map, the existence of which we want to prove. And we can even compute the derivative. And its derivative is given by, so the derivative is actually how our solution depends locally on our parameter changes, is given by a formula that I will directly write down, and we will prove it actually later, or quickly and easily. So I write it like this. So d f x star of A with respect to A, and we evaluate that whole thing at A bar. This is given by an expression that is taken, interestingly, this Hessian matrix, that thing that should be positive definite, but with an inverse. Fortunately, that exists, right? Because it's a positive definite matrix. Times the derivative with respect to A of the gradient of this thing at the point x bar and A bar. So this thing we want to prove, and the mathematicians, or maybe everyone, can maybe guess what we will probably use, which theorem will help us here in order to prove that. I already start the writing of the proof. Maybe I start actually writing here. So if you want to prove that something, it's a very implicitly defined function, right? This x star, it is an implicit function actually. And so we will use the implicit function theorem, which actually many of you might have heard about. So who has heard about the implicit function theorem before? Also in analysis, which one? 2, 1? Yeah, okay. Mm-hmm. So we use the implicit function theorem. Yeah, I think I will do it a bit more explicit than in the script. So what we will actually do is we will define a root finding problem for the function which is just the gradient. And so I will define a function that I call g of x and a, and which is just the gradient with respect to x of f at x and a. So this is a function because f is twice continuously differentiable. This g will still be C1. So it's a function in C1. And this function I will now use. Actually, the funny thing is, what is this g? So g is a map from from D, but D is a subset of Rn cross Rm to Rn. Yeah, where D is element in Rn subset. So it's a map which has all the things that we need for the implicit function theorem. Namely, it has some unknowns here, and the same number of conditions here. And so we look at we know that G at A bar, at X bar and A bar is equal to 0. I mean, that's our assumption, right? Gradient was 0. And in the implicit function theorem, the only thing that we need is that actually the dg with respect to dx at the point where we look at should be invertible. So that's what we need. Is it a non-singular matrix? And so we can compute it, and here we have the gradient. We need to differentiate it again with respect to the variable x. So this thing is actually the second derivative of f with respect to x. And this is indeed invertible at the point because of our assumption here. And then the rest actually is implied by the implicit function theorem. So there's one thing about this, which is this formula. This formula actually is something that's also part of the implicit function theorem, and so I could just recall it. I will just first write it in terms of G, and then I will, because it's beautiful and it helps us to remember that formula, I will also derive that formula and not just say we apply the implicit function theorem, which I do for the existence. So this formula actually says that dx star by dA is equal, and I omit the argument here, to minus dg by dx to the minus 1 times dg by dA. That's what the implicit function theorem says, and if you just plug in the definitions of this function g, then you get this formula here. So that's clear. But how do we get this formula, and how do we remember it? And I think it's a nice thing to remember what we want. What this whole implicit function theorem implies is actually that g of x star of a, comma a is equal to 0. That's what the implicit function theorem ensures, namely that this function exists. And when we want to look at the derivative and learn about the derivative of this thing, then the easiest way is to just differentiate that thing again, now that we know existence, which I didn't prove, but I relied on that theorem, of course. But once we do it, we can actually now differentiate that whole thing. And what we get is dg by dx, the partial derivative, times the inner derivative, which will be dx star by dA, plus the partial derivative dg by dA. And because when we differentiate this thing and it will be 0, then the derivative will of course also be identically 0 everywhere. So we know that this formula will hold for the derivatives. And if we just use the fact that this thing is an invertible matrix, it will be equivalent to that formula. Okay? So we just bring this thing to the other side, that gives the minus sign, and then we multiply it with this inverse, and that gives this inverse. So this formula is not magic or something. It's easy to remember by just taking this definition of the implicit function and differentiating at once and saying that the whole thing is 0. And what is nice about this formula, and in particular the one that we see above, is that we directly see that this sensitivity of our solution with respect to our parameter depends on the inverse of the Hessian. So we see directly that if there would be a 0 eigenvalue on the Hessian, we could have a big problem here. And this wouldn't be invertible anymore, or the derivative has a very high likelihood that it would go to infinity. Yeah, because we have an inverse of that Hessian matrix. So please keep in mind, you need a positive definite Hessian, so that means the second order sufficient conditions, in order to have a non-infinite derivative of your implicit function. Intuitively, this is very easy to illustrate, and I did that in another lecture. Some of you have been there, but anyway, when you have an optimization problem where your optimizer is or your minimum is a flat minimum. That means that there is, in one direction it might be positively curved, but in the other direction, the one that you see now, it is not. So I have a two-dimensional optimization variable, I have this optimization landscape, and I have a minimum which is completely nice, but it's actually flat, so there is no derivative in this direction. It's zero derivative in this direction. And if now someone starts to add a little bit to this problem, a little gradient, for example, just perhaps a little bit this problem, then it might actually turn in this direction or in this one. And if you would just imagine a little ball in the middle, it would not find its minimum very easily. It would just roll very quickly to the other side. And that is exactly what would happen if you don't have curvature. But if I have nice curvature, like if you take a muesli bowl or something, right? You take it, you put a ball inside, or maybe, I don't know, what do you put inside? Little small tomato or something, and then you move your bowl, it will always have a nice location. It will not change its location very quickly. Yeah? So that's what this theorem says, and the main quantity that decides everything here is the second order derivative of your Hessian. So that is the thing that needs positive eigenvalues. Please remember. Okay? We will have it actually in the next chapter. We will encounter problems where this doesn't hold. Other questions regarding the theoretical conditions we derived and did until now? If it's not the case, then I suggest that we directly go to the first application class of problems that I think I want to look at. And these are estimation and fitting problems. I just realized one thing. We have Friday afternoon, of course, and we want to stop at 3:45, right? And I should not forget about that. I think of it. But let's still use the time to introduce the class that we will talk about on next Tuesday. And it's giving you an example of optimization problems, and they are unconstrained. And what we want to look at are functions which have a special form where this f of x, the objective function, is actually given by the difference of two things squared. So we take some model, we subtract some data which we call very often eta, and we take the Euclidean norm and square it. So that's a very specific form of objective function, but one objective function which very often appears in applications. So we have a vector m, a vector valued function m. So m is a function from Rn, from our decision variables, into some other vector that I call in the script Rm. And we call it the model, or sometimes also the forward model. Why it's called the forward model? It's like with primal and dual, so things are only forward if there is something else which is an inverse in that case. The whole problem to find the best parameter x that makes the m output as similar as possible to the eta output is called an inverse problem. But the task of computing the output m of a model for some input parameters x is sometimes also a very difficult task, and it's actually the task of simulation methods. So people play with input parameters and then they get some output. So this is what all some simulation engineers, so to say, do. And because it is a task in itself and can be a very complicated function, we will sometimes call it the forward model. I mean, already to evaluate that m might be a very expensive and elaborate procedure. But we assume that we can do that and that this m is even differentiable. Actually, we will assume even C2. Okay, and eta are just data. And yeah, one way to think of this whole thing is very often we have some plots where we have maybe some different indices. I here could just take the index I, could be time or something else, and then here are the values that our model would predict. So these would be the values. If this is 1, 2, 3, 4, 5, then these would be the components M1 of X, this would be component M2 of X, and so on. And what we want is actually that our model that could have different outputs if we would have different parameters X, then the whole thing would look different. But that it looks similar to some data that we obtained, which could be these things. And these are the measurement data. So that would be eta 1, this would be eta 2, this would be eta 4, eta 3. Yeah, and what we want to minimize is actually the distance between these two. Oh, this was the wrong plot, sorry. So these differences we compute, this is this distance in a vector form, and then we square them and we add them up, and then we have this expression here. So that is what a least squares fit does. So that's called a least squares cost function. And where would we have that? We have it in many fields, and I just want to outline a few of them. Maybe some of you have encountered these problems already in some other context. Don't know. You can give examples. Yeah. I think you had this example in the right. So there was some function approximation. Just say what you.
Regression.
Sorry.
Regression.
Okay. In regression we have it, of course, exactly. Data regression, fitting polynomials and so on. There was also one of the optimization problems where someone wanted to fit the impedance or something, but he isn't here now. Yeah, but sometimes you want to match something, so you have a technical system that should have some function that should look like something that you have. It's also used in function approximation. So you might sometimes want to approximate one function with another function which is easier. It's sorry. Classification. You can use it a lot. Yeah, actually, it's like a precondition for classification. But it is used in classification, absolutely. It's generally used in all type of parameter estimation. We will come back to that. And it's also used in what we call state estimation. And state estimation is the task of determining the state of a system, which could be a big or a small system. I mean, it could be that you observe something like a pendulum that's swinging. You just take position pictures, but you would like to know to estimate its velocity, which you can then try to estimate using the comparison of a simulation with the data that you got. But it could also be that you have a model of the weather, for example, the climate or the weather on Europe, the clouds and the air and how it moves, and you want to estimate in which velocities the air has, and so that you can predict the velocities, speeds, air pressures, and so on, based on all the measurements that you have. So then the measurements are lots, of course, in weather forecast, and also the decision variables are lots, so it's a huge problem, but it's still a least squares cost function at the end, very often. So this whole system to minimize f, or minimize this fit of a model, minus eta square. This optimization problem is called an inverse problem. And why is it called inverse? Because it is actually answering the opposite question from this one. This one, the forward system says, given some parameters, what would be the outputs? So the inverse says, given some outputs, what could have been the parameters, the input parameters that would have led to these outputs? So that's why it's an inverse problem. So these are called inverse problems, and they are an important source of optimization problems. I think we will not do the linearly squares today. It's too interesting to do it just quickly at the end here. And we just stop a bit earlier. Okay, so I wish you a wonderful weekend.